for gravity waves, which was very successful, as you all heard from the news, and which produced something astoundingly new here in Pisa at Virgo, and I'm sure we'll hear about it. The next, I will just end my brief introduction here. I just want to remind you that the next colloquium will be held on April 18, and it will be devoted to biology, neurobiology in particular. My colleague Andrea Ferrara will continue here with a short presentation of our guest.
So good afternoon. It's a pleasure for me to be here and to be able to introduce a very eminent Italian scientist, Giovanni Losurdo. And so a brief, only short introduction to his very long and successful career. So Giovanni is, first of all, is a researcher at the National Institute for Nuclear Physics here in Pisa, and he essentially fell in love with gravitational waves when he was very young, essentially a child, when he started his thesis on gravitational waves under the supervision of another very eminent scientist, Adalberto Giazzotto, who unfortunately passed away last year. He's definitely the father of gravitational waves, and in turn one of the most eminent Italian scientists of the last century. I think there is no doubt about that. For Giovanni, today is a little bit coming back because he used to be a PhD student here at the Scuola Normale. So we are proud to say that Scuola Normale has also contributed a little bit to the success of Virgo and the gravitational wave detections. But after that, after being here as a student, then he moved in the US, in several places actually, where the enthusiasm and the activity in gravitational wave was rising. He has been in Caltech, MIT, University of Western Australia, in Tokyo, and also in Glasgow. Then in 2006, he started to work very hard on this idea of improving the performances of Virgo, the interferometer, which, as you know, is located a few kilometers away from here in Cascina. And so the idea was to build an advanced version of this interferometer, which is called Advanced Virgo. And the goal was just to achieve a much better sensitivity, about 10 times better than Virgo could provide at that time. So this activity lasted for 3 years, and then in 2009, I was appointed as the principal investigator of the instrument. So he became essentially the boss of the experiment, and it was it was, I guess, very tough because he had to coordinate about 200 people, ranging from scientists to engineers to people with very different skills, and also part of international collaboration that involved 5 different countries: Italy, France, Netherlands, Poland, and Hungary. And so he has been very successful in that. And as I said, because the task was very difficult, he had to coordinate people with different expertise. And in fact, Giovanni had to deal with things like optics, solid-state physics, and cryogeny, and vacuum chambers, and all that stuff. So very tough PI role. And actually, for these achievements, Giovanni has been awarded last year the Galilei Prize for Science, and so this is a very important prize that essentially is a recognition to his outstanding research work. Finally, we know that Giovanni has got, at that time when he was probably almost a postdoc or an ending PhD student, he got offers from the US. Particularly, we know that there was an offer from Stanford that he did not accept because at least that's what he says, that he wanted to come back and contribute to Italian and European science. And therefore, we should be very grateful to him also for this, because together with all of us here is trying to keep the excellence of Italian research at the cutting edge of in the worldwide competition. So it's a pleasure to introduce Giovanni. Thank you.
So, first of all, thank you very much for the kind words, and I'm really grateful for this invitation because it gives me the chance to come back. Last time I've been in this room, from this side of the room, it's been a few years ago to defend my PhD thesis, and at that time I was trying to convince, Virgo had not been built yet, and I was trying to convince the panel that we were going to realize an experiment capable of opening a new window of the universe. And this was taken with sympathy, but also with a lot of skepticism, because it appeared really as an enormous experimental challenge. And Adalberto Giazzotto used to see in the last 2 years, we have seen that 2 groundbreaking discoveries have been done by the gravitational waves interferometers. The first one in September 2015 was the first observation of gravitational waves ever, 100 years after the Einstein's prediction of their existence, and the latest in August 2017, the observation of binary neutron star coalescence with the identification of the optical counterpart and the following astrophysical observations. These 2 discoveries certainly open a new era in the observation of the universe. So the original vision of the fathers of the field have found eventually an evidence. And that's just the beginning of the path. I would like to start quoting the initial lines of a great scientific paper that was issued 4 centuries ago, the Siderius Nuncius. I will read them in the Italian translation, which is nicer than the English one. Grandi cose per verità in questo breve trattato propongo all'osservazione e alla contemplazione di quanti studiano la natura. Grandi, dico, è per l'eccellenza della materia stessa, è per la novità non mai udita da secoli e infine per lo strumento mediante il quale queste cose stesse si sono palesate al nostro senso. Galileo was talking of his instrument, the cannocchiale, thanks to which he had discovered Jupiter's satellites, starting in this way a revolution not only for science but also for philosophy and politics and religion. But basically there was the idea that a new instrument that he had made more performant had been capable of opening a new window on the universe of that time. And the same is happening now with totally new instruments, which are the detectors of gravitational waves, which are again allowing surprising discoveries. Don't look too much at the equations. I just want to remark that we have a theory which explains gravity. It's the general relativity of Einstein. And the theory is based on a number of highly nonlinear differential equations that are very difficult to solve, but can be solved analytically in a few cases under some approximation. One of these approximations is that when you are far from big masses, in a region of space-time that you can consider basically flat, then these equations become linear, and they admit a wave solution. And this wave solution is basically a small perturbation of the space-time metric, a ripple on the space-time, which propagates at the speed of light. There is a big problem with this equation, and the problem is that this constant, which appears here, is g over c to the fourth, so the Newton constant divided by the speed of light at the fourth power is very small. It's 10 to the minus 44 in standard units. And this can be read in different ways, but basically means its intrinsic meaning is that you are looking for effects which are very small, and so if you want to look to these effects, this will be a big experimental challenge. The idea at the basis of a detector, especially an interferometric detector, is that if you have a ring of test masses which are in free fall in the space-time and they are hit by gravitational waves, this shape will be deformed in the two orthogonal directions alternatively. And the effect that we want to measure is a delta L, so the variation with respect to the radius of the ring, which is proportional to the amplitude of the gravitational wave. Now, I will divide this seminar in three parts: detectors, observation, and perspectives. About the detector, so going back to the concept I was explaining before, you have this ring of freely falling masses which is deformed by the passive waves, and you want to measure the effect with the best sensitive method that you have so far. So using light to investigate the position of one of these test masses. So you replace test masses with mirrors and build a simple Michelson interferometer and try to measure this variation. And you see that the effect you have to measure, when you assume realistic values for H, which come from astrophysical consideration, you find values of the order of 10 to the minus 21. So in order to amplify your effect, you need to build an interferometer with a baseline, an arm length as long as possible. But realistically, what you can make is build kilometer scale interferometer. And then you are left with an effort to be measured of the order of 10 to the minus 18 meters. So basically, you want to measure the displacement of macroscopic objects, like the mirror, at the level of 1,000th of the proton diameter, 1,000th of a Fermi. So that's the concept. The first step to go from concept to an experiment was worked by Rainer Weiss, who is this man here, was awarded Nobel Prize last year. And he wrote a paper, which is basically the main reason why he was awarded the Nobel Prize, where he described how a real interferometer could be realized. He discussed all the noise sources which would have spoiled the sensitivity of such detectors. And amazingly, this remained an internal note on an MIT review that was never published. That's interesting because if you ask him why you didn't publish that, he says, at that time we were used to publish experiment results, not just plans on future experiment. And it's interesting to see how things have evolved since then. Then, in 1989, we started to go from concept to project because two projects were put forward simultaneously to the funding agency. The proposal for a LIGO interferometer in the US and the proposal for a Virgo interferometer in Europe. It was 1989. Well, I will not go into the details, but basically what you easily find out is that a simple Michelson interferometers will never be enough to measure the effect you want to measure. So you start complicating the design. First of all, you start adopting some optical tricks, make the optical configuration more complex. For instance, you force your photon to jump back and forth about between two mirrors. You trap them for a relatively long time in order to lengthen the time in which they interact with the gravitational wave, and in this way amplifying the effect, then you understand that this mirror can be just sit on ground, but they need to be isolated from ground vibration. So you start designing and building sophisticated system for isolating them from external vibration. Then you find out that you need a vacuum system and that you need to lengthen the arm as much as possible, and you start coming closer to a realistic detector. This was the process, and at the end of this process, after many years of research and developments, years of fighting with bureaucracy, fighting for funding, 4 detectors were built. The 2 LIGO in the US, which were part of the same project, and the idea was to have 2 interferometers on the 2 sides of the United States at the distance of 3,000 kilometers, in such a way to be able to make coincidence and so be able to make a more reliable detection. Then there was Virgo in Italy, 3 kilometers long, a bit shorter than LIGO, and then a smaller one in Germany, Geo 600, just 600 meters, which made him basically not competitive with the other 2 detectors. And this interferometer worked and took data in the first decades of this century. Each rectangle here is a run of data taking. No detection was done, but a rich legacy was then invested into the second generation detector. Something else very important happened in that time. First of all, both LIGO and Virgo reached the design sensitivity. And this was absolutely not obvious at the beginning because these machines were completely novel and nobody could be sure that they would have worked as planned. And moreover, they demonstrated a very high duty cycle. So the machines were very stable. Virgo, for instance, had during data taking had a duty cycle of more than 80%. So they prove also to be reliable instruments. There is another aspect in this plot. You see the blue curve is the Virgo sensitivity. Virgo has been, in all this era, the most sensitive detectors in the low frequency range. And this was one of the basic idea behind Adalberto Giazzotto's proposal. He was convinced that there was a lot of interesting physics to do in the low frequency range. And therefore, he developed the super attenuator here in Pisa. In many years of studies, he developed this because this was a highly super performant vibration isolation system for the mirror, capable of cancelling the seismic noise by many orders of magnitude already at low frequency, and in this way capable of widening the bandwidth of the antenna towards the low frequency. At the time, he was thinking that this region was interesting mostly for the periodic sources like the pulsars. But the recent discoveries have shown that there are black holes of mass larger than expected, and that this region is very important to detect these black holes to accumulate signal-to-noise ratio for these sources. So there was a vision behind that finally paid off. There was another fundamental step in that decade that it was, let me say, a political one with a highly scientific fallback, because LIGO and Virgo had started their operation as experimenting competition. But then they realized, and again, a lot of merit goes to Adalberto for this, they realized that the maximum of science would have been done only establishing a network of interferometers working together. The main scientific reason for this is that the response, the antenna pattern of this detector is not directional. They have some blind spots, but other than that, they have an almost omnidirectional response. So a detector by itself cannot determine the direction of the source. And in this way, if you don't know what is the location of the source in the sky, you don't do astronomy. And while having 3 detectors together allows triangulation and localization of the sources, so they LIGO and Virgo decided to make an agreement for full exchange of data, joint data analysis, joint publication policy, and this is really an important step in the gravitational wave science, but not only, because it gives also a good example of how a scientific collaboration can work. A step back, again back to 1989, to the LIGO proposal, there was a very interesting aspect in this proposal that already there, the concept of an advanced detector which would have improved the LIGO sensitivity by an order of magnitude was present. And this was fundamental because as the National Science Foundation decided to fund the LIGO project, they were also buying this concept. And this set the framework for substantial R&D funding to develop technologies to second generation version, and was crucial to realize a few years later the advanced LIGO and advanced Virgo detectors. And in fact, already in 2003, while the operation of the first generation was just starting, the LIGO laboratory put forward to the National Science Foundation a proposal for advanced LIGO, which was fully funded for above $200 million 5 years later, in April 2008. This was funding the equipment for 2 interferometers to be installed in the existing infrastructure, plus the ones for a 3rd interferometers to be shipped to India, which has now committed to realize the infrastructure for so-called LIGO India. The construction was completed in 2014, and the first run started in September 2015. And it's now history that just a couple of days after starting data taking, they made the first detection. Advanced Virgo is an analogous upgrade of Virgo to a 2nd generation detector, and the funding was approved 2 years later with respect to LIGO for about 22 million euros. So the budget is much smaller with respect to the LIGO ones, although some differences in the accounting should be taken into account. For instance, this is investment only, while LIGO also accounts for manpower. The project was formally completed with the start of the ETO run in August 1, 2017. And it's interesting to notice that the time from the funding to the start of data taking is exactly the same for the 2 projects, and also the time between the funding and the first event detected is exactly the same. So for us, this is a reason of pride because we have done a successful project with much less resources. There is a lot of technology behind this success, starting from the mirrors. The mirrors are really a jewel, and the improvement in mirror technology from in 10 years from Virgo LIGO to advanced Virgo, advanced LIGO has been striking. It's enough to think that the surface of this mirror is flat at the level of about 0.2 nanometer root mean square. It's an amazing achievement, and this is one of the key which allowed to improve the sensitivity going from Virgo to advanced Virgo. Then these mirrors are suspended through thin silica wires in order to reduce as much as possible the vibration due to the intrinsic mechanical fluctuation, the so-called thermal noise, which are less with this material. Then they are embedded in very complex mechanics, which allows also their controls in feedback, and suspended from vibration isolation system, the super attenuator I was mentioning before. A lot of complex optics is needed to, let me say, manipulate the beam, make it of the wanted shape and size. And all the photodetectors that we use to detect the signal are as well seismically isolated and acoustically isolated, because they are kept in vacuum in order to get rid of a lot of stray noises which can affect them. And the entire system is in the largest volume of vacuum that we have in Europe. These pipes are 3 kilometers long and 1.2 meters in diameter, and you reach ultra vacuum at the level of 10 to the minus 9 millibar inside. So there is a lot more to be told, but I go to the next topic, which is the observations. So on 14 September 2015, the two LIGO interferometers that had just started taking data recorded these two signals, which have a very good overlap at 3,000 kilometer distance. This was received with a laugh, let me say, because everybody in the collaboration looking at this plot was convinced that there was not a real signal, but this was rather a blind injection. Blind injections was a technique that we were using as a stress test of the data analysis chain. So there was a committee of 3 people who secretly decided to inject artificial signals in the data. And this it was done in such a way that the data analysis team had to recover the signals to check that everything was right on the data analysis side. So everybody was thinking of a blind injection, but in fact it was soon clear that couldn't be the case because the system was not yet working. And it was just astonishing, because everybody was hoping to see a signal, but nobody could ever hope to see such a beautiful signal with an extremely high signal to noise ratio and an extremely high statistical significance. There is more wonder about this, and the signal was very close to what had been modeled years before as a waveform generated by the coalescence of 2 compact stars. And what's nice of these sources is that despite general relativity is a very difficult theory, but in this case you can compute very accurately the waveform you expect using almost the Newtonian theory with some relativistic perturbations. And then instead, in the region where the 2 masses come closer and then merge, cannot be treated in this way, and is instead computed thanks to the recent surprising developments in numerical relativity, which have been made possible by the development of supercomputers. And what's really striking in this signal is that the predictions that come both from post-Newtonian theory and both from numerical relativity fit very well the experimental data, which is considered as a very strong test of the Einstein theory in a strong field regime, which had been inaccessible so far. This is such a relativistic regime that at the moment of merging, the 2 black holes have a speed which is 0.6 times the speed of light. And this is astonishing because we are talking of objects which have a mass of respectively 36 and 29 solar masses, which are moving at 0.6 speed of light. Moreover, out of the waveform you can measure the distance, you can measure the redshift, and you can measure that there is an energy radiated in gravitational wave of 3 solar masses. So 3 solar masses vanish and are transformed into gravitational waves. And the peak luminosity of this source exceeds 10 to the 56 erg per second, which makes this event the most luminous event ever observed in astrophysics. So, thanks to, it was the first time we observed many things. So, it was the first direct detection of gravitational waves, the first direct observation of black holes, the first observation of the larger known stellar mass black holes, because nobody was expecting black holes with mass higher than 25 solar masses. The first observation of a binary black hole system, the first observation of a binary black hole merger, the first test of general relativity in strong field conditions. And I would add another consequence of this observation is that it demonstrated that the ground-based interferometer were the right instrument to do this kind of science. After these events, more black holes, more binary black holes were detected. And if you put them in a chart as a function of the mass, here the surface is proportional to the mass, you see that the blue ones, which are the ones detected through gravitational waves, give the hint of a different population with respect to the purple ones, which are the black holes known through X-ray emissions of gas falling into them. So that's food for brain for the astrophysicists. Then, on August 1st last year, Virgo joined the LIGO during the observation run 02. And then finally, there were 3 2G detectors acting as a single machine. Here I'm using a single machine was an expression, again, spelled out for the first time by Adalberto Giazzotto, who was trying already in 2000, in the year 2000, to convince the community that there was a lot to gain by putting together the data of the 3 interferometer, and instead of analyzing each interferometer output by itself, consider them as a single stream of data, vectorial stream of data. Because in this way, by doing a coherent analysis, you increase also the signal-to-noise ratio that you can get. And so this is the network that we have now. Then I marked here the position of Kagra, the Japanese detector, which will come online probably in 2 years from now, and LIGO India here, which will come online in mid of the next decades. So eventually we will have a 5 network detector. Unfortunately, all these detectors are in the northern hemisphere. It will be very interesting. There is a strong scientific case for having also a detector in the southern hemisphere, and I really hope that Australia could sooner or later realize it. It's not the end of the story, because beside the gravitational wave network, there is a so-called multimessager network. So basically, the LIGO-Virgo collaboration have signed agreement with more than 90 group of astronomers and astrophysicists who agreed to receive the LIGO-Virgo triggers and follow them up. So the idea is I have a candidate recorded by the 3 interferometer. With the data of the 3 interferometer, I can quickly produce a so-called sky map. So I can quickly identify a region in the sky where I'm pretty confident the source is located. And so I give this information to optical telescope, radio telescope, X-ray and gamma ray satellites, what else? Infrared, and even neutrino detectors. And they point to that region of the sky and check for an electromagnetic counterpart, which is very interesting because we know that there are sources which are expected to emit at the same time gravitational waves, neutrinos, and electromagnetic waves. It was not easy because the community of astronomers is not used to collaborations. They are always smaller groups in strong competition between them. So it required some work to realize this. Let me make a quick summary just to give you an overview of the data taking period that we had. So we had the first O1 run, observing one run between September 2015 and January 2016. And the second run, which started in November 2016 and was concluded at the end of August 2017. And in these red bars, only LIGO was running, but at the end of the O2 run, also Virgo was joining, and it was an overlook of the three detector sensitivities. Virgo came up with a sensitivity worse than LIGO for two reasons. First of all, because there is a structural 3/4 factor due to the length of the interferometer, which makes Virgo intrinsically less sensitive. And second, because Virgo came online with just 3 months of commissioning. Commissioning is the period of time that you devote to improve the sensitivity. But anyway, on just a couple of weeks later, there was a first event detected by the 3 interferometer. And this was certainly an historical moment. Again, it was a binary black hole, which was detected by the 2 LIGO and Virgo. As you see, the signal is weaker in Virgo because the detector is less sensitive, but still very visible. It was important for several reasons. The main one is that if you compare the localization of the source that you can achieve with just the 2 LIGO, which is this banana, to the localization that you achieve once you add a third detector, which is this gray spot here, you see that you improve from above 1,000 degrees squared, which is a surface certainly too wide for the astronomer to follow up, to a few degrees squared. You also improve the estimation of the distance, and overall, if you put together this improvement, you see that the error box on the sky in which you locate your source is reduced by factor 30. This is a great progress because you start be interesting for the astronomers follow-up. But just by comparison, this is the localization of the first detection, the source emitting the first gravitational waves ever detected. And there was a lot of attempt to find an electromagnetic counterpart there because it was the first time. You see, each of these green square represents an observation by one telescope, and you see that you need hundreds of observations in order to cover the entire area identified, which makes the follow-up very long, and you may lose very interesting information. So reducing this area is crucial to do some serious follow-up. There was another aspect, this is a slide just for physicists, let me say, that this gravitational wave, like electromagnetic waves, can be polarized. And there is some fundamental physics behind that, because general relativity, Einstein theory, only foresees 2 states of polarization, tensorial states of polarization, but there are alternative theories of gravity which foresees also scalar or vectorial polarization. So for the first time it was possible to tell something, and it appears from the analysis that general relativity is favored with respect to alternative theories. So in summary, this was the first event seen by Virgo, the first event with a small sky localization area, and the first event allowing polarization studies. So we were happy because Advanced Virgo had just come online, and we had been awarded with this beautiful measurement, but there was not even the time to celebrate that. Just 3 days after, there was it, and it is a fantastic signal lasting almost 100 seconds, which is associated to the gravitational waves emitted by the coalescence of a binary neutron star. The signal to noise ratio was very high. It is the loudest signal so far. It is interesting that the signal in Virgo is basically invisible, while it's very visible in the two LIGO. And there are just two possible explanations. Either the detector doesn't work, or there is something else. But the detector had just worked 3 days before, so there was a good confidence that it was still working. The reason was different. It was these antennas, like I said before, have some blind spots. And the blind spots, the orientation of blind spots depends on the orientation of the detector. So this was the antenna pattern for the two LIGOs. And this was the antenna pattern for Virgo. And if you combine the response of the three interferometers, you see that the only way to see the signal in LIGO the way you've seen it, and the signal in Virgo basically absent, is to assume that the source is located here, very close to a Virgo blind spot. This is what comes from more complex analysis. And paradoxically, not seeing a signal in Virgo allowed a better localization of the source. And in fact, the source was the source position was identified with an accuracy of less than 30 degrees squared, which was very small, relatively very small, and so very easy to follow up. The initial alert went out 27 minutes after detection. But before going to the astronomical observation, let me say again a couple of things mostly addressed to physicists. The fact that you can measure the signal for such a long time allows you to measure the main parameter ruling the waveform with impressive accuracy, because you measure the so-called chirp mass, which is a combination of the two masses in a way that is really very, very accurate. It's more difficult to say what is the value of each single mass, because there are degeneracies over other parameters. Also you can measure the distance, which is about 40 megaparsecs, so much closer with respect to the black holes that have been measured before. Now, if this is a binary neutron star, the current model says that you should expect, first of all, the emission of a short gamma burst, and second, a so-called kilonova, that is the isotropic thermal emission produced by radioactive decay of rapid nucleon capture elements, the so-called air process. So basically what happens is that the two neutron star merge, a lot of materials is ejected around the source, and this material is very rich of neutrons, and there are the ideal conditions to synthesize nuclei which are heavier and heavier, and which are intrinsically unstable because there are too many nucleons there. So these nuclei decay radioactively and emit radiation, and this radiation should be observed in some way. Amazingly, a gamma ray burst was detected by Fermi GBM 1 second after the events. In fact, the announcement of the gamma ray burst came first because Fermi has a public release of their events. They continuously announce announce detection of gamma burst. It was one among the many, but this became immediately interesting after the detection of gravitational wave signal was announced. And this made the astronomers go crazy, really very excited. And then the next hours, the optical count, so all the telescopes were pointed in the region. All the telescopes were pointed in the region identified by LIGO and Virgo, and as the night arrived in Chile and it was possible to observe, the optical counterpart were found in a galaxy called NGC 4993. And this follow-up was followed up for the next days, and a lot was learned by this observation. I will tell something more on this, but first of all, let me give you an outlook of the physics which can be done by this observation. First of all, the waveform, these kind of sources are so-called standard siren. So the amplitude of the waveform recorded on Earth gives a direct measurement of luminosity distance of the source. Identifying the optical counterpart gives you the possibility to know the redshift, which is generally found in proper tables. And so you can have a direct measurement of the Hubble parameter, which is independent, with a method which is independent from the cosmic scale ladder of distances. And so this measurement was done. And here it is marked, the colored regions, the colored area mark the value of the Hubble parameter published by Planck and by the RISC group. It is well known that there is a tension between the two measurements. Our measurement for just in between is not sufficient to solve the controversy. And moreover, the error is still pretty large, and this is due to different contributions. First of all, there is an uncertainty of the redshift due to the peculiar motion. Second, there is some degeneracy depending on the inclination of the source, which adds a considerable error on the measurement of the luminosity distance. But we will do better in the next. So this just gives the flavor of the fact that these observations will have something to say on cosmology as well. Then there was a measurement of fundamental physics, which was pretty amazing because the almost simultaneous arrival of gravity wave and gamma burst allowed to make an estimate on the speed of gravity. Do gravitational waves travel at the speed of light as predicted by Einstein? Well, we have a difference in arrival time of 1.7 seconds over a travel of 130 million years, which is amazing. And even if you do conservative assumption on the distance, you put yourself in the worst case for the distance, and also assuming that a delayed emission of the short gamma burst with respect to gravitational wave, you see that you constrained that the speed of light and the speed of gravity are equal in 1 part over 10 to the 15. What else? A kilonova. So this is the evolution of the optical spectra observed. There have been many observations with different instruments. This is the one done by the group of Elena Pian. And what's interesting is that the spectrum that you measure starts with thermal emission, and then as it evolves and fades down, it starts seeing structures. And these structures can be put in relations with the formation of heavy elements. So these heavier than iron, this observation is considered as the first elements that in binary neutron star merging there is formation of elements heavier than iron, like up to lanthanide and uranium and so on. Which had been modeled before, but now there is some experimental measurement. You can also do nuclear physics, namely neutron stars have a very interesting laboratory for nuclear physics, because basically we know very little on internal structure and core position. The theorists describe the property of a neutron star using an equation of state, which basically tells what is the relation between pressure and density, or if you want, between the mass and the radius of the stars. And there's a heap of models, and nobody knows which is right. But now the interesting point is that the equation of state can be observable through gravitational waves, because this is related to how the star can be deformed when exposed to a tidal field. So you have two stars very close to each other, and the gravity field of one star deforms the second stars, and since it is deformed, this is a quadrupolar moment which contributes to the gravitational wave emission. So in principle, the waveform emitted by neutron star is different if the star is highly deformable or lower deformable. So this should be visible. Unfortunately, at this stage, you see that the differences in the two models fall into a range of frequency where the sensitivity of the current detectors, this is advanced LIGO, is not enough. So we expect to learn more as soon as we improve the sensitivity of the detectors at high frequency. And we expect to say something on the equation of states of the observed neutron star. Indeed, something was already published in this sense. So the data of this observation already allow to say that the radius of the stars we have seen must be less than 14 kilometers. And now let me again go back to 1989. It's interesting to go back and forth, because you can really, once you see the scientific result and you compare them with the vision of the fathers of the field, it's really impressive. In the introduction of the proposal, of the Virgo proposal, Alain Brienne and Alberto Giazzotto were writing, Virgo must be considered both as an experiment and as a step towards a future observatory. The long-term goal is that of being one component of the gravitational wave detector network, which will involve other detectors in other countries and provide data of astrophysical interest. So you see already then, when basically they want to build a detector by themselves in competition with the others, but they were already thinking to the future. And then generated international effort required by the birth of gravitational wave astronomy. There is still, there is really a great vision behind, and I think that only with this is very educational, I will say, that the realization of experiment which lasts 30 years can only stand if there is a strong vision behind. Now, when Galileo observed Saturnus with his cannocchiale, he drew it in this way. So he was understanding there was something funny with this planet, but he could not resolve the ring. He just was saying that was a kind of trilobate structure. And then 400 years later, we have this image of Saturnus taken by Hubble, where you can even see a polar aurora, so you are seeing the effect of cosmic rays in Saturnus' atmosphere. So 400 years, and with gravitational waves, now we are here. We are at this stage. So it's clear that it's just beginning, and we need to develop it further. And I'm using here the Planck image because clearly the ultimate goal is understanding the early universe. That's the holy grail of this research. The case for better detector is very simple. The number of events we measure is proportional to the cube of the distance at which we can look at. So basically, this is the sensitivity of the detector times the observation time. And 1 day of data at range of 80 megaparsec, so advanced LIGO in O1 could see a binary neutron star as far as 80 megaparsec. And 1 day of data at this range is equivalent to 64 days of data at 20 megaparsec, which was the LIGO sensitivity in 2009. So observing for a long time is good, improving the sensitivity further is better. Just to give you an idea, this ball represents the volume of universe which could be observed by Virgo in 2011, last August, where the volume had been increased by factor 10. And we are improving the detector because in fall, next fall, in September, when the O3 run will start, this volume will be again increased by a factor 10. Having an international outlook, you see, so in fall there will be a new run by LIGO and Virgo, both with improved sensitivity, which will last about 1 year. So we expect a fair number of detections inside this run. Then the Japanese will come online later. And then LIGO India will be added in 2024, according to expectation. So overall, in a few years, we will have a network capable of localizing more than 60% of the sources with an accuracy of better than 10 degrees square. And this number can become 100% or close to 100% if a detector in the southern hemisphere is added. So, what next? We are already working to a set of upgrades capable of enhancing the sensitivity of LIGO and Virgo by factor 2, let's say, make them a 2.5 generation detector. The timeline for this is 2023. But the real next step is the realization of new infrastructures able to host third-generation detectors capable of doing measurement of cosmological interest, which means gaining 1 order of magnitude with respect to the advanced detector. The timeline for this is 2030, and there is also a scale factor in the cost, because the cost will go above $1 billion or euros. There are at the moment two proposals. Well, one is almost a proposal, the second is more a concept. Again, Europe is ahead in this search for a 3G detector, because we have this Einstein telescope project, which foresees to realize an underground infrastructure hosting three nested detectors, which are by themselves able to resolve the polarization of the waveform. The reason why it should be underground is that we want to extend the bandwidth further towards lower frequency, in such a way to access even larger masses. And this requires to suppress by several order of magnitudes the natural ground vibration, which can be achieved if you go underground. Then there is another project in the US for a 40-kilometer interferometer on surface. This is another view of the NStyle telescope with the 3 nested interferometer, and this is the enhancement on sensitivity one wants to achieve. So a factor 10 basically in all frequency range, and a factor 10 also in the bandwidth. It's interesting that recently the new so-called APEC roadmap, so APEC is a board trying to coordinate the efforts on astroparticle physics in Europe, sees the Einstein telescope as the main investment for the next decades, while CTA, the Gamma Observatory, is the main investment for this decade. Clearly, this does not mean that the project will be done, because APEC is giving recommendations, but is not giving money. So then there is the problem where to find the money. In this context, I want to say that Italy wants to be candidate for hosting the infrastructure. And the candidate site is a Sardinian site in Barbagia that you see in this photo. It's interesting because Sardinia is geologically very stable, and the microseismic noise in this site is 3 orders of magnitude better than the one in Virgo. Moreover, as you can see from the photo, there is no anthropogenic noise because there is basically nothing there. Although there is a lot of expertise in digging because there are mines. Recently there has been a strong endorsement by the Italian government, the Regione Sardegna, University of Sassari, and INFN. And there is also money available to start the geological investigation and accurate geological investigation and characterization of the site. So we will put forward this candidature will be a strong from the scientific point of view, because of the low noise of the site, and it will be very interesting also from other points of view, because we believe that having a big research infrastructure in Italy is still very important, both from the cultural point of view, because this convey education, high-level education, and are capable of transforming the imagination of the new generations, and this way can be transformative for the whole society. And it's important that this can happen in Italy as well. And it is also a good, very important occasion of cultural and economical development for Sardinia, which really needs it. Then there will be also on a similar time scale, LISA. I have just this slide because basically there is no time, but LISA is a very exciting project which will observe gravitational wave in a completely different and complementary range of frequency with respect to ground-based detector. And they also have achieved a couple of years ago a spectacular success with the results of LISA Pathfinder demonstrator. So, gravitational wave detectors are finally making science, after many decades of detector development, a new window of the universe has been opened. GW170817, the binary neutron star, has offered a spectacular preview of the science to come from the worldwide Multimessager network of observatories. The gravitational wave network will be enhanced with the addition of new detectors and improvement of the existing one, and we have plans for a third generation detectors targeting the early universe. I would like to really conclude by quoting a part of an article which has been written by a person whom I don't know personally, but was written just a few days after the announcement of the first detection on the Bollettino of Scuola Normale. And this is interesting because it was written by a philologist of Scuola, Francesco Morosi. I have it in Italian. E allora perché è importante la scoperta? Ci saranno certo implicazioni scientifiche cruciali, ma non è per questo che ci fa così impressione. Questa scoperta ci sembra così importante perché è fatta bene. Per arrivare a questo risultato centinaia di uomini e donne hanno lavorato al massimo della loro creatività e della loro precisione. Questa scoperta ci impressiona perché abbiamo, come genere umano, spinto le nostre conoscenze oltre il limite, oltre un limite quasi impensabile persino per lo stesso Einstein. E questo è un atto di bellezza, una vetta della creatività umana. Thank you for your attention. I'll take your questions.
Thanks a lot for this illuminating talk. I have a question concerning the next improvement that you have announced for in a few months, September. Do you plan to improve by reducing the thermal noise of the suspension fibers, for example, and in which frequency range if you do that, and if you do that by using fused silica rather than metallic fibers, how do you manage with electrical grounding of the mirrors? Thank you.
Okay, so the improvements to fused silica fiber has already been implemented. We are suspending the last of the 4 mirrors these days. And probably I should say a few words on this. Advanced Virgo was supposed to start with the mirrors suspended through silica fibers. This was a technology that had been used already in Virgo before, well before LIGO. But then suddenly, as soon as we started to remount the mirrors with this fiber in Virgo, they started breaking. And they started breaking, and they were breaking when the mirror was in vacuum. And there has been a lot of research to understand the reason of that. We have re-scrutinized each step of the production of this fiber, the material, the way we manipulate them, and all the tests were negative. We weren't able to find any fault in the process. But still they were breaking, and so we were forced to, in order to allow the experiment to start, we were forced to suspend the mirror with steel wires, which was making the sensitivity in the low frequency range worse. But eventually, I saved the details, but eventually we found that the problem was due to a contamination of the vacuum system. There was basically small polluting particles produced by some pumps, which through a very funny mechanism were injected at high pressure in the vacuum chamber and were hitting the fibers. So eventually we understood this, we solved the problem, and now we have suspended all the, at least 3 meters out of 4 successfully using silica fiber. So this will lead to a significant improvement below 100 Hertz. It's not the only thing we have done. We have also increased the laser power, and we have also added a squeezer provided by our German collaborators in order to increase the sensitivity at higher frequency. So overall, we are confident that a significant improvement can be done.
About the future that you mentioned, of course, to improve the sensitivity is important, but I imagine that there might be, I wonder whether they exist already, there are already ideas on specific physics goal that one should aim to. And if there are, how they influence choices of detectors and things like that. Is the question vaguely clear or not?
Yeah, it's very clear. And okay, so the main scientific goal is to see as many sources as you can. So reach a sight distance at redshift 10, 20. So detect sources at cosmological distance, and see the ones that you are already seeing with a signal-to-noise ratio so big that will give you every details of the waveform. In this way, you will become able to discriminate between alternative theories of gravity or measure the equational state of a neutron star. There's a lot that one can imagine when you become able to make detections with very high statistics or looking very distantly. For instance, let me make just an example. There is a recent paper by a Spanish theorist, I don't remember the name at this moment, which claims that we are detecting primordial black holes. and that this can be these primordial black holes, so formed during the Big Bang, before the era of stellar formation, can be a significant part of the dark matter. Well, you cannot discard or demonstrate this until you are able to see a black hole existing before the star formation era. So these are the kind of scientific goals that one can have in front. How do they influence the choice of the design of the detector? Well, I think that one big lesson from the recent observation is that the lower can go in frequency, the better, because at low frequency you access bigger masses, or you can observe coalescing binaries for a big number of cycles. And so, although it is very challenging from the experimental point of view, I think it's the most difficult challenge ahead, and it's not granted that we will really able to make an Einstein telescope working down to 1 Earth. It's not granted. It has to be. It is underground, but it's not sufficient. You need also to improve the performance of the vibration isolation. And you need also to show that you can get rid of the so-called Newtonian noise. The Newtonian noise is the direct coupling of ground vibration. So ground vibration produces local fluctuation of the density of the ground. And so there is a fluctuation, a stochastic fluctuation of the G vector. And this couples directly to the mirror, so the short circuit the vibration isolation. And there can be a limiting factor at a limiting noise at low frequency. We are already developing techniques for modeling this noise. So you surround your mirrors with a network of hundreds of accelerometers. And analyzing coherently the data from this sensor, you can try to understand what is the movement of the rocks around you, and so what is the noise that it produces, and subtract it for the data. We are going to do the first tests in the next couple of years on this at Virgo. But it's still to be demonstrated that in the end you will be successful. So it's a challenge. We need R&D.
Before I ask my question, I should say I'm a chemist. So I would like to know, so how big is the amplitude of the gravitational wave close to the event? And how much would I be stretched if I was standing next to the event?
Okay, so the concept of next to the event is a bit, requires some discussion, because next to the event there is no gravitational waves. You start having big deformation of the space-time, but then in order to be able to talk of a wave, you have to be a bit further from the source, in the so-called radiation area. And then the same happens for electromagnetic radiation. It's the same mechanism. But then about the amplitude, you have to consider that what we measure, that is an amplitude, is a strain, fades as 1 over the distance, and not as 1 over the distance squared, because we measure amplitude and not power. And this is the reason why, if we increase the sensitivity by 10, we increase the detection rate by 1,000, because it goes with the cube of the distance.
If you manage to deploy the space-based observatories to our intuition, because they are so larger, they should be far better than ground-based ones. Would they be better than ground-based ones? Would be they so much better that you then ground-based observatories have no role, or still, even with space-based ones, still there are other reasons why they're not so much better?
No, it's wrong to make a comparison of these two detectors in terms of better or worse, because they observe in different range of frequencies. So they will be complementary. And being complementary means, for instance, that consider a binary black hole of very large masses, say 1,000 solar masses for each black hole. So LISA will be able to observe the orbital motion of these black holes and tell ground-based detectors, look, in a couple of years, 5 years from now, you are going to see the coalescence of these two black holes. So in principle, there is room for synergy. In terms of absolute sensitivity, it's difficult to compare because they have different noises. But like I said, they will be complementary, I mean, it's wrong to say that one is better than the other.
If we happen to have any corrections beyond general relativity, for instance, higher order terms in the Einstein-Hilbert action or something like that, what would be the chances of spotting them in the gravitational wave signal?
I'm not sure to understand the question.
If we have any effects, any gravitational effects beyond general relativity, like the R-squared terms in the Einstein-Hilbert action or something like that, then...
I don't know. Well, it's an interesting question, but yeah, should be rather asked to a theorist. I don't know. Probably with very high signal-to-noise ratio, so in the future generation, you might be able to explore such effects. I doubt that with the current detectors you can.
Okay, thank you.
You're welcome.
I'm not sure I understand your bounds on the speed of gravity. There was an upper bound and a lower bound.
A bound of what?
On the speed of gravity.
Yes.
Why was the lower bound not 0?
So the lower bound assumes that the distance. So you measure a luminosity distance of 40 megaparsec plus 8 minus 14. So you are assuming that you are at the lower level of the fork. So you are at the distance of 26 megaparsec, which means that they have traveled for less time, and so you have so the relative error on your measurement is bigger. So in this sense, it is conservative. And the upper bound comes from the fact that you are assuming that the gamma ray burst is emitted 10 seconds after gravitational waves. And again, this is conservative because in the current model, 10 seconds is the maximum gap allowed. But likely, the gap in the emission is lower. And it is conservative because if you assume that there are 10 seconds, you are saying that light has, let's say, started 10 seconds later and arrives 2 seconds later, so it's going faster than gravitational wave. In this sense, it's conservative. But still, with this assumption, you get this surprising constraint.
Okay, thank you.
So let's thank our speaker, and then there are some small refreshments somewhere around. Thank you.
Grazie a voi.